Hi, in this video we're going to cover hash tables, and you can kind of think of hash tables kind of like dictionaries. The difference is that with this hash table we're going to create the actual code for this, which kind of shows you how dictionaries work behind the scenes. So let me pull up, get a blank file here that we're going to use, and I'm going to open up the book that I've been using for a class. Like I've said before, this is a um, open source book, problem solving with algorithms and data structures. You can find it out on internet. There. So, okay, so I'm going to go ahead and just kind of read through this with you here. Previous sections, we were able to make improvements in our search algorithms by taking advantage of information about where items are stored in the collection with respect to one another. For example, by knowing that a list was ordered, we could search in logarithmic time using a binary search. In this section, we will attempt to go one step further by building a data structure that can be searched at O1 time. This concept is referred to as hashing. In order to do this, we will need to know even more about where the items might be when we go to look for them in the collection. If every item is where it should be, then the search can use a single comparison to discover the presence of an item. We will see, however, that this is typically not the case. A hash table is a collection of items which are stored in such a way as to make it easy to find them later. Each position in the hash table, then often called a slot, can hold an item and is named by an integer value starting at 0. For example, we will have a slot named 0, a slot named 1, a slot named 2, and so on. Initially, the hash table contains no items, so every slot is empty. We can implement a hash table by using a list with each element initialized to the special Python value none. Figure 5.4 shows a hash table of size m equals 11. In other words, there are m slots in the table named 0 through 10. Okay, so here's the figure here that kind of shows you what it looks like. And what we're going to do is we're going to take these items and hash them to this table. And the reason for this is, let's say that nobody ever does this anymore, but let's say that you have employees and you want to store them by social security number. Well, to do a one-to-one correspondence, you'd have to have a list of 1 billion items. And if you only had 40 employees, it's wasting a lot of time. So you cut the list size down to hold the 40 employees. Say you use, let's say, 61 as an example. So you have room to grow in there. Okay. Well, there's possible that you could get 2 social security numbers. I mean, really possible to get two social security numbers that would hash to the same location. Okay, so we're going to talk about that later, but this is where we're going with this. So the mapping between an item and a slot where that item belongs in the hash table is called the hash function. The hash function will take any item in the collection and return an integer in the range of slot names between 0 and m-1. Assume that we have the set of integer items 54, 26, 93, 17, 77, and 31. Our first hash function, sometimes referred as the remainder method, simply takes an item and divides it by the table size, returning the remainder as its hash value. H item equals item mod 11. Table 5.4 gives all the hash values for our example items. And that's what we looked at up here. Okay. So we have 10, 4, 5, 6, 0, 9. Those were the hash values that we got, the remainders. Note that this remainder method modulo arithmetic will typically be present in some form in all hash functions, since the result must be in the range of slot names. Once the hash value has been computed, we can insert each item into the hash table at the designated position, as shown in figure 5.5. We'll look at that in a minute. Note that 6 of the 11 slots are now occupied. This is referred to as the load factor and is commonly denoted by that little symbol there equals the number of items divided by the table size. For this example, the load factor equals 6 over 11. Now, when we want to search for an item, we simply use the hash function to compute the slot name for the item and then check the hash table to see if it is present. This searching operation is O1 since a constant amount of time is required to compute the hash value and then index the hash table at that location. If everything is where it should be, we have found a constant time search algorithm. You can probably already see that this technique is going to work only if each item maps to a unique location in the hash table. For example, if the item 44 has been the next item in our collection, it would have a hash value of 0. 44 mod 11 equals 0. Since 77 also has a hash value of 11 or of 0, we would have a problem. According to the hash function, 2 or more items would need to be in the same slot. This is referred to as a collision. It may also be called a clash. Clearly, collisions create a problem for the hashing technique. We will discuss them in detail later. So there's the example here of the list with the numbers in there and the slots that still have none. Given a collection of items, a hash function that maps each item into a unique slot is referred to as a perfect hash function. If we know the items and the collection will never change, then it is possible to construct a perfect hash function. Refer to the exercises for more about this. We're not going to worry about that here. Unfortunately, given an arbitrary collection of items, there is no systematic way to construct a perfect hash function. Luckily, we do not need the hash function to be perfect to still gain performance efficiency. One way to always have a perfect hash function is to increase the size of the hash table so that each possible value in the item range can be accommodated. This guarantees that each item will have a unique slot. Although this is practical for small numbers of items, it is not feasible when the number of possible items is large. For example, if the items were 9-digit social security numbers, this method would require almost 1 billion slots. If we only want to store data for a class of 25 students, we will be wasting an enormous amount of memory. That's what I talked about at the beginning of this. So our goal is to create a hash function that minimizes the number of collisions, is easy to compute, and evenly distributes the items in the hash table. There are a number of common ways to extend the simple remainder method. We will consider a few of them here. The folding method for constructing hash functions begins by dividing the item into equal sized pieces. The last piece may not be of equal size. These pieces are then added together to give the resulting hash value. For example, if our item was the phone number 436-555-4601, we would take the digits and divide them into groups of 2, 43, 65, 55, 46, 01. After the addition, we get 210. If we assume our hash table has 11 slots, then we need to perform the extra step of dividing by 11 and keeping the remainder. In this case, 210 mod 11 equals 1. So the phone number hashes to slot 1. Some folding methods go one step further and reverse every other piece before the addition. For the above example, we would get 43, 56, 55, 64, and 01 for 219, which would hash to slot 10. Another numerical technique for constructing a hash function is called the mid-square method. We first square the item and then extract some portion of the resulting digits. For example, if the item were 44, we would first compute 44 squared equals 1936 by extracting the middle two digits 93 and performing the remainder step. We get 593 mod 11. Table 5.5 shows items under both the remainder method and the mid-square method. You should verify that you understand how these values were computed. We can also create hash functions for character-based items such as strings. The word cat can be thought of as a sequence of ordinal values. C is 99, A is 97, and T is 116. Okay, so there's an example here. There's the remainder, and then there's the mid-square. Right? And then this is the comparisons. This is the of the remainder of mid square. This is the hashing a string using ordinal values to do that. We can then take these three ordinal values, add them up, and use the remainder method to get a hash value. And this shows the code for doing that, which we're not going to mess with on here. It's just an example there. So it's interesting to note that when using this hash function, anagrams will always be given the same hash value. To remedy this, we could use the position of the character as a weight. Figure 5.7 shows one possible way to use the potential value as a weighting factor. The modification to the hash function is left in an exercise, so we're not going to worry about that part of it. You may be able to think of a number of additional ways to compute hash values for items in a collection. The important thing to remember is that the hash function has to be efficient so that it does not become the dominant part of the storage and search process. If the hash function is too complex, then it becomes more work to compute the slot name than it would be to simply do a basic sequential or binary search as described earlier. Okay, so collision resolution. We now return to the problem of collisions. When two items hash to the same slot, we must have a systematic method for placing the second item in the hash table. This process is called collision resolution. As we stated earlier, if the hash function is perfect, collisions will never occur. However, since this is often not possible, collision resolution becomes a very important part of hashing. And so this is talking about that here where we have, back up here a little bit. Well, that's doing the cat stuff and everything. We don't want that. Collision resolution, but this is the linear probing that it's going to be talking about here in just a minute, where what we will do is when it hashes and has a collision, it will go through until it finds an empty slot to put it in. And then there's another way of doing that also. So one method for resolving collisions looks into the hash table and tries to find another open slot to hold the item that caused the collision. A simple way to do this is to start at the original hash value position and then move in a sequential manner through the slots until we encounter the first slot that is empty. Note that we may need to go back to the first slot circularly to cover the entire hash table. This collision resolution process is referred to as open addressing in that it tries to find the next open slot or address in the hash table. By systematically visiting each slot one at a time, we are performing an open addressing technique called linear probing. Figure 5.8, which we just looked at, shows an extended set of integer items under the simple remainder method hash function 54, 26, 93, 17, 77, 31, 44, 55, 20. Table 5.4 above shows the hash values for the original items. Figure 5.5 shows the original contents. When we attempt to place 44 into slot 0, a collision occurs. Under linear probing, we look sequentially, slot by slot, until we find an open position. In this case, we find slot 1. Okay, and then it goes to another example with 55 doing the same thing, which gets placed into slot 2, and then another one with 20 that goes into slot 9 is full, so it goes down. We visit slots 10, 1, 2, and finally it's empty slot in 3. Once we have built a hash table using open addressing and linear probing, it is essential that we utilize the same methods to search for items. Assume we want to look up the item 93. When we compute the hash value, we get 5. Looking in slot 5 reveals 93, and we can return true. What if we are looking for 20? Now the hash value is 9, and slot 9 is currently holding 31. We can simply return false, since we know that there could have been collisions. We are now forced to do a sequential search starting in position 10. Okay, and so then they go down here and kind of show how that worked on there. So, okay. Disadvantage of linear probing is the tendency for clustering. Items become clustered in the table. This means that if many collisions occur at the same hash value, a number of surrounding slots will be filled by the linear probing resolution. This will have to have an impact on other items that are being inserted, as we saw when we tried to add the item 20 above. A cluster of values hashing to 0 had to be skipped to finally find an open position. This cluster is shown in figure 5.9. Once we are, one way to deal with clustering is to extend the linear probing technique so that instead of looking sequentially for the next open slot, we skip slots, thereby more evenly distributing the items that have caused collisions. This will potentially reduce the clustering that occurs. Figure 5.10 shows the items when collision resolution is done with a +3 probe. This means that once a collision occurs, we will look at every third slot until we find one that is empty. So the general name for the process of looking for another slot after a collision is rehashing. With simple linear probing, the rehash function is new hash value equals rehash old hash value, where rehash position equals position +1 mod size of table. The +3 rehashes, you do position +3 on there. Okay. It's important to note that the size of the skip must be such that all the slots in the table will eventually be visited. Otherwise, part of the table will be unused. To ensure this, it is often suggested that the table size be a prime number. This is the reason we have been using 11 in our examples. A variation of the linear probing idea is called quadratic probing. Instead of using a constant skip value, we use a rehash function that increments the hash value by 1, 3, 5, 7, 9, and so on. Okay, so this gives you some more examples of all this. This one here is one that I think I really like a little bit. This says it's collision resolution with quadratic probing. No, this isn't the one I want. But I was thinking of, and they may not talk about it in this book, is that each one of these slots, instead of it being a primitive value, use it as another list. So if you have two numbers that hash to the same location, the first one would go in position 0, the second one would go in position 1. So then when you're looking for your value, you're just looking through a few of them and not having to look through the whole table to find a particular value. Okay, so I guess that's this one here. That an alternative method for handling the collision problem is to allow each slot to hold a reference to a collection or chain of items. Chaining allows many items to exist at the same location in the hash table. When collisions happen, the items is still placed in the proper slot of the hash table. As more and more items hash to the same location, the difficulty of searching for the item in the collision increases. But it's the same thing if you have a lot of them that hash to the same location. You're looking through the complete table to find the location of where it is, and that could take a while to do also. So they all have problems with this. So we're going to talk about implementing the map abstract data type. One of the most useful Python collections is the dictionary. Recall that a dictionary is an associative data type where you can store key data pairs. The key is used to look up the associated data value. We often refer to this idea as a map. The map abstract data type is defined as follows. Okay, so what you have in here is you have a structure of an unordered collection of associations between a key and a data value. The keys in a map are all unique so that there is a one-to-one relationship between a key and a value. So the operations you have as map is to create a new empty map, passing in a key and a value. You add a new key value pair to the map. If the key is already in the map, then replace the old value with the new value. Get, passing in a key. Given a key, return the value stored in the map or none otherwise. Del for delete. Delete the key value pair from the map using a statement of the form del map and then in brackets key. Len for length. Return the number of key value pairs stored in the map. In, return true for a statement of the form key in map if the given key is in the map, false otherwise. Okay. So one of the great benefits of a dictionary is the fact that given a key, we can look up the associated data value very quickly. In order to provide this fast lookup capability, we need an implementation that supports an efficient search. We could use a list with sequential or binary search, but it would be even better to use a hash table to describe above, as described above, since looking up an item in a hash table can approach O1 performance. So that's what we're going to do now, is we're going to go ahead and create this dictionary, or this hash table, sorry. And that's what I got this here for. So we're going to create a class, hash table class. So in here, we're going to have our INIT, and we're not passing anything out in except for self. Okay. So self.size, in this case, is going to be equal to 11. And now that value would change every time you had more items that would fit in there. So you would probably want to come up with a better way of doing this, like letting them enter the size for this, because if you do this every time you want to increase the size, you have to go in and physically change the value stored here in the class. So self.slots is going to be equal to none, and we're going to do that times self.size. So we make, in this case, 11 slots, 0 through 10, with value none in there. And our data, type this in here, there we go, is going to be equal to none times self.size. Okay, so that's our INIT. Next one we're going to do is the put function. And so the hash function, let's see, the collision resolution technique is going to be linear with a +1 hash function. The put function assumes that there will eventually be an empty slot unless the key is already present in the self.slots. It computes the original hash value, and if that slot is not empty, it iterates the rehash function until an empty slot occurs. Okay, so we're going to go ahead and put this in here. So to do this, we need the key and the data. Hash value is going to be equal to self.hash function. And we got to pass in the key and the size, which is going to be the length of self.slots. So if self.slots hash value, and that should be, sorry, bracket, equals none, then self.slots hash value equals key and self.slots hash, self.data hash value equals data. Else, if our self.slots hash value equals key, then self.data hash value equals data. This would be a replacement on this one if that happens. Else, next slot equals self.rehash hash value length of self.slots. Okay. So then while self dot slots next slot does not equal none, so we haven't found an empty one yet, and self dot slots next slot does not equal key. And let's spread this out a little bit more here. There we go. Next slot equals self dot rehash next slot length of self dot slots. Okay. So first part up here is if it equals none, we just put the stuff in there. Otherwise, we need to check to see if it matches, and if it does, the key, then we're just replacing the data. Otherwise, we need to rehash to find an empty slot to put it in. Okay. So that's all the put on there. Oh, no, it's not either, sorry. Into that, so now we're down here, let me back up here to this while loop here. We're outside that while loop. If self dot slots next slot equals none, then self dot slots next slot equals key, self dot data next slot equals data, else self dot data next slot equals data. Okay, so that'd be a replacement again on that. So now we come over here and we got our hash function self, key, and size. And so then we're going to return our key mod size. And then we have our rehash self old hash size, and then we're going to return old hash plus 1 mod size. Okay. So the next thing is the get function. This begins by computing the initial hash value. If the value is not in the initial slot, rehash is used to locate the next possible position. Notice that when we get down here, I don't have line numbers on here, but line 15 guarantees that the search will terminate by checking to make sure that we have not returned to the initial slot. If that happens, we have exhausted all possible slots and the item must not be present. So the final methods of the hash table that we're going to put in here too provide additional dictionary functionality. We overload the get item and set item methods to allow access using brackets. This means that once a hash table has been created, the familiar index operator will be available. Okay, so let's put this in here. This is our get. We put pass in a key. Start slot is going to be equal to self.hash function, passing in the key and the length of self.slots. Look at something real quick. Okay. Then data equals none. stop equals false, found equals false. Okay, then position is going to be equal to start slot. So while self.slots sub position does not equal none and not found and not stop, if self.slots position equals our key, found equals true, data equals self.data position, else position equals self.rehash, passing in position and the length of self.slots. So now if position equals start slot, meaning we got it all the way back to the beginning again, stop equals true, because we ran through the whole thing, we couldn't find a place for it. And then we come back out to the while loop here and we return data. Okay, so if we return none, that means we didn't find it. Okay, got the two small ones here, def underline underline get item, underline underline, self and key, and then we're going to return self.get, passing in key, and then def underline underline set item, underline underline, self key data, and this is to self.put key data. Okay, that's the entire class. I'm going to go ahead and save this. And I need to create a folder here. Save, and then save it in here, and I'm going to call this hashtable.py. Save that in there. Okay, now I've got a little test program that I'm just going to open up and show you instead of typing this all in. So let me open it up here. Okay, so what this is going to do here, we're going to create a hash table object, H, with using the underline get item and underline set item. We can do this like this. So H of 54 is equal cat, 26 is dog. So this would be like, this is the key, and this is the value we want to store in there. Okay, so once we have all these entered, we're going to do a print of h.slots. Then we're going to print it h.data. Okay, then we're going to print h20 and print h17. We're going to set h20 equal to duck, so we're changing that value. We're going to print then h20, and then we're going to print the data again. Okay, let's go ahead and run this. And this is what we get. There's the values. I'm going to put this over here to the side so you can kind of see this. 77 went to 0, okay, because 77 divided by 11 is 7 with a remainder of 0. 44 is in slot 1. It went to 0 also, so it went to 1. 55 also would have gone to 0, so it's in slot 2. There's 20, 26, 93, 17. We have 2 nuns, a 31, and a 54. So here's the values, the data that was stored in there. Then when we did the print H dot slots, okay, I'm sorry, that was those things up there. Then we printed H20. Okay, H20 was the chicken, which you printed. 20 is right here. Then we printed H17. H17 is right there. H17 is the tiger there. Okay. We then changed H20 to duck, and we printed H20. Then we printed the data, and there's the duck in there. Okay. So I'll kind of show you how this works. Now, like I said, this is how the built-in dictionary works when you use that. So I wanted to go through the underlying way of this works so that you can kind of see this and how this operates. So look this over, and hopefully you got some information out of this. Bye.